Hello. How's it going, everyone?
Yeah, hi. I think I should be audible now. Can you hear me?
Yeah, I can hear you.
Yeah, that's great. Then let's do a quick video test. Yeah.
I can also see you.
Maybe I'll just yeah. It should be fine, I guess. It should be easy to share the screen. Yeah, hold on.
Yeah, there should be a button at the bottom saying share screen.
Yeah, I see the button, but I may try to disable the video while I'm sharing because yeah, just let's do like just screen sharing test. Yeah, and I think the presentation should be visible. Is it visible?
Yeah, I can see it now. Awesome.
Yeah, that's great. So are we waiting a bit longer or just?
Yeah, usually we wait like until like 3-4 minutes past 6 as people are entering.
Yeah, I just stopped like sharing the screen for a moment.
Sure. Nice Christmas sweater, Chris.
Handmade by my friend's mother in Norway. Honestly, why are you laughing?
Your cat approves. It was like perfect timing.
She does. She also disapproves of moving too much, apparently.
Does she also have like a Christmas sweater, a tiny one?
No, she would kill me if I put her in any type of clothes. Like we tried doing the harness a while ago, like a couple of years ago. She hated it.
I think it would be worth like the Christmas card.
Sorry?
I think it would be worth the photo on the Christmas card, like you and her matching sweaters.
I actually might try that for this year's postcards / Christmas cards.
I'll be expecting one.
You got it. Is there a return address on the package?
I think so.
Okay, good.
Yeah.
Did you? Your background is different. Like the rocket that's very close to you used to be on the other wall.
Yeah, this piece of furniture finally arrived. Like we ordered it like a long time ago, and it's like finally here.
Is that a Tilco?
No, it's what's the name of the company? It's like a Berlin company. Stukobo.
Oh,
It's essentially like Lego. So you buy blocks and then you can stack them the way you want.
we got one of these for the office, but it was like a different company. I just suppose that there's many of them.
I guess it's not like a revolutionary idea to have like building blocks for furniture. Cool. So people are slowly coming in. How is it going, everyone?
Nice.
Great.
Going pretty good. How about you?
I'm fine, thanks. You opened a PR on Evaluate, right, last week?
Yeah, that's me.
But it's nice to put a face on a PR.
Thanks for all the help. I'm sorry for the bumbling. Almost.
Oh,
done,
no
though, I think.
worries. Yeah, I think like there were some tests failing, but it wasn't your fault. It's like the CI at the moment is like very annoying. Gonna change it. Cool. Let's maybe wait another minute or so.
Yeah, honestly, to be fair, I'm yeah, I will just turn my webcam on for a moment. I'm just happy that we did that test, and the reason why is because when I decided to run the Zoom decided to self-update, so I was waiting a bit at the beginning.
Classic Zoom.
But I mean,
It's like the thing that always happens to me on the Mac is like if you use a platform the first time, you have to say like this application is allowed to use your camera, and you can only do that when you like restart the application.
yeah, at some point in my career, I was just like running Arch Linux, and it was nice to like decide when you can update. Then I decided to like switch to Microsoft stuff, and I decided to be greeted by a Windows update. And I was thinking that I'm done, like Windows Update got better, but honestly, recently I was in the middle of doing something and Windows Update suddenly decided to reboot the system and I lost everything, so.
Yeah. I always really hated when Windows does that to you, like forcing you to update. It's like, I'm grown up, I can decide myself when I want to update. I don't want to be told like you have to update in an hour.
Yeah, I think in the enterprise edition there's like there is an option to like turn it off for a while, like I think like 2 weeks maybe. I'm not sure, like at least it was like for Windows 10 Enterprise, but yeah, I was basically thinking to some extent how much is like the end result of like having like the same product pretty much both for enterprise and for customers, because I mean there's like the separate like licensing tier like Windows 10 Enterprise, or now with Windows 11. I'm not going into that, but basically it's still like the same Windows at the end of the day. But yeah, maybe not. Let's not dive into the great days of like Windows Millennium.
Yeah, today's reading topic is like Windows XP, the best Windows.
95.
Cool, I think.
No, wait, Nate. I'm not gonna let that pass. 95 is the best Windows. What are you talking about?
How old are you, Chris?
Almost as old as you. What are you? Aren't you like 23 or something?
No. I'm 30. 31. Anyway, let's go back to the topic. I think we waited long enough. Welcome everyone to, I think it's the fourth edition of the reading club by now. It's like going really fast. Today, Tomasz, is that the right way to pronounce your name?
It's Tomasz.
Tomasz kindly agreed to give like a brief overview of the named entity recognition chapter. So I think like without much more introduction, I hand over to you. I think you mentioned that we can do it kind of like interactively and use like your presentation kind of as a starting point for discussions and questions.
Yeah,
So-
the goal of the presentation is more like to facilitate like the talks and like discussion, and not to like go like linearly like from the beginning to end. So I will try to launch the presentation. I will like disable the video to like just make sure I'm not like overutilizing the bandwidth. Hold on.
You can also, if you have like questions during the talk, you can post them in the chat and I can try to kind of like sort and facilitate them.
Yeah, great. And the presentation should be visible, right? Can you see it now?
Yes.
Yeah, that's great. I just try to launch maybe full build. Yeah, that's great. Yeah, so I decided to analyze pretty much like the chapter 4, which is like multilingual name entity recognition, and without like longer details. I wanted to like focus on like the big picture, and this is why I separated linguistics, the models, and the details. And the reason why is because as I was reading the book, I was finding myself like focusing on like some of the like implementation details, and I was losing like the big picture. So that's why I pretty much decided to like extract linguistics, the models, and then like maybe like talk about details if anyone wants to. So I so I decided like a bit like in on me. So I pretty much like started with pretty much AWS and software engineering. Then I decided into Azure and data engineering. And even though at this point like people are asking me why why I would decide to do so, because like I would say in 2017 it wasn't quite like extreme to do like data engineering with Azure or like generally like data stuff in Azure. But at this point, I was like kind of like predicting what would happen and how now pretty much Microsoft is like doing like the data stack. And at this point, it was interesting to see Microsoft experimenting with open source like data stuff. Basically, like pretty much they were trying to like implement Hadoop on their products, and they were pretty much like playing with that. And I kind of expanded into like mixing that also to some extent with law and ethics, and this includes like licensing stuff, or basically the stuff at the pretty much at the edge of like I would say ethics, law, and machine learning. So for example, I was recently researching how easier it got to like swap faces in machine learning models, and as a result, how easy it is to swap faces when people don't want to be like their faces to be swapped, like some like gray areas around that. But yeah, I would not go into details. I'm also like hosting machine learning news Twitter Spaces, and we pretty much like covered last time the fine on Discord and what was happening there, what has been happening in France, especially with data protection. And if anybody wants like to know further or join the next Twitter Space that we are hosting, I also like included the QR code, and I can guarantee that the QR code is safe because I was entering myself. So at least it should be. So and there are like other ways to like contact me on Twitter, on Mastodon. Oh, I did the typo. Like, never mind. I should include another ampersand. So yeah, but never mind. And I also like blog on the website. So yeah, after this intro, let's go into So I decided to start with linguistics, and the reason why is because the chapter focuses on the language situation in Switzerland, and I got the impression at the beginning that I didn't kind of I would say grasp the languages. So I decided to like extract like 3 like or I would say 3 key like sentences. And the idea is to extract like key sentences from the languages and have them like at the same time like in different languages. And the goal is to like have like a grasp of how languages is processing. And the context of the chapter 4 is that basically in the chapter 4, pretty much what was happening was fine tuning it on German, and then pretty much wondering why it translates, or why the model performs better when it's when the model is done in German and it's trying to one-shot French. And I was like, as I was thinking about that, why it was happening, I was just like analyzing languages. I decided to pretty much summarize it by this. And the reason why is because I came into a conclusion that the reason why the model pretty much is performing better between German, French, and Italian, and it's not performing great on English, is because pretty much English doesn't have like gender articles this much. I would say like there are some I would say specific scenarios when it's gendered. And I was basically thinking while going through this chapter like that something that I was wondering about is basically that even though like NLP abstracts it away to some extent, like it's the job of the model to extract those patterns, it still like requires some language knowledge. Oh, hold on a moment. Yeah, bonus point for spicy memes. Yeah, but basically I was basically thinking that even though like it was kind of I would say explaining the book, I was kind of like missing like the linguistics part, and I was basically wondering that even though as I was saying, the job of NLP is to like figure out the patterns, there's still like some like gray area between like the model figuring out the patterns and you like fine tuning the model, and then I was basically hold on, because I think the presentation got blocked for a moment. Yeah, great. So as I was basically going, I was thinking that this is like the point about like articles, that basically this was the reason why the model was performing worse. And to and as I was going, I was also thinking that one of the issues as I was going the book was basically realizing that I kind of forgot what was the goal of the model and what was happening with the model. So that's why I decided to separate like that pretty much the base model was pretty much created from the common crowd data. And pretty much the interesting part about common crowd data is that it was data gathered through like crawling websites. And the interesting thing about that is that there are some like legal issues around that. And the reason why is because pretty much the legal basis for correcting common crowd data is fair use, and some people are not happy. And the reason why, because fair use is pretty much the way to extract copyrighted data and use it like for purposes, while pretty much not like I would say respecting copyright or not. Basically, some people are not happy that like copyrighted data is used at the basis of fair usage. So this is like something that I observed, and that to some extent was controversial, but yeah, pretty much that was the story behind XLM Roberta, that the data like from crawling the internet was gathered. And I decided to like also like separate what was happening with fine tuning. So pretty much the idea was that we have like the base model, pretty much the base model that was gathered from the common crowd data. And then we fine tuned it on the specific task. And in this case, the task is pretty much multilingual name entity recognition. And we trained for like non-stringle data. And what I found probably like the most interesting about that is that basically we can train only on one language. Basically, we can fine tune it on one language, but at the same time, we can also fine tune it in multiple languages. So at the end of the day, I would say the kind of like the interesting part was that even though the starting point was like multilingual model, we can just fine tune it on single language, and we can still like receive quite decent results, except as I was going before about the spicy meme, basically that if we fine tune on German, then English performs worse, but French is still good. So yeah, I was trying basically to like summarize and as I was going, I realized that something that I was missing like through like I would say the entire reading of the book is that pretty much that there is the Roberta model in the Hugging Face. There are also like more like specifics models, and there is also Matt X mentioned that as a way pretty much of like training the model like bigger. And this is something that I wanted to mention, especially if someone went through like the book and realized that where are the models. So I wanted to mention that aside from the Roberta that's like in the Hugging Face, there are also like the models that were trained. And this is something that I wish it was like I like pointed out in the book more, because I realized that there are models, and it took me like a while to like got to the models that were trained in the chapter. So it's pretty much the number 2 if somebody didn't realize that it's there. And this is like something that I realized as another part as I was trying to like differ. And this is like as a shout out to Patrick Verplaten from Hugging Face, who was pretty much kind of the reason why I discovered that, and the reason why is because I spotted on Twitter. And the interesting part about like doing the multilingual stable diffusion is that is the stable diffusion, but the basic part is also based on Roberta, and there are some languages supported. But the interesting part is that I mentioned languages supported, and this is because the base model Roberta supports around 100 languages, and the stable diffusion model from Hugging Face, or I would say the stable diffusion model that's there supports like less languages. Like for example, I was trying to generate images in German, and it took me a while to realize that German is not supported. So this is the reason why I was still like mentioned it, and it was interesting to see that like how another model can be based for another model, and that was like pretty much it for what I was preparing that as an intro. If anybody like has more questions or wants to dive into other directions. Oh, and I wanted to like mention that kind of the reason to do like PowerPoint was because PowerPoint has also like nice automated capability to generate slides. So this was pretty much also, yeah, I can pretty much like automate the process. So it was like kind of the reason also why I decided to go with like PowerPoint.
Thanks a lot. And thanks for the hidden advertisement for Microsoft and Office. But it's cool. Are there any questions or things that you would like to discuss?
Andrew,
Or nothing? Yeah.
could you
Hey,
or
Andrew.
somebody else give some a few lines of a summarization about the training of the modulingual, each English or all I'm sorry I didn't finish. I did not read the chapter before I was running out of time. If you can give a few lines of summarization about the modulingual training, that would be great.
Sure. Yeah, I mean, so in 3 sentences, roughly, what the chapter is about is like you can use a model like XLMR or XLM Roberta that's been pre-trained on many languages. So it has been pre-trained on roughly 100 languages with the same goal as BERT, essentially. So you just predict like masked words. But if you do that on many languages, you kind of like profit from this cross-lingual transfer that we've been kind of discussing in the chapter. And what we show is if you take a model that has been pre-trained on many languages and you fine-tune it on even just one language, for example, doing named entity recognition or sentiment classification, it can generalize to the other languages that it was pre-trained on. It's like if you speak 2 languages and I explain to you what sentiment classification is in one language, you might be able to transfer it to another language. And these multilingual language models, they're kind of similar. And what's kind of interesting is you can even sometimes beat a monolingual model if you have like this cross-lingual transfer and you have a lot of resources in some languages that kind of are surrounding. I hope that summarizes it a little bit.
Okay, so when training with a multiple language, I guess you just randomly pick up some articles from each language versus, you pair them up with the translation. For example, you might have 2 articles, one in English, one in German, or it's exact the same article translation, but I guess that's not the way to go, right? You just pick up random article for the training, right?
Yeah, so I think there have been several approaches. There have been models that kind of used alignment. So where you have some data that is in multiple languages and then you align the data, the sentences, for example, in English and French, and you do some masked language modeling using both sentences. So the model has kind of to translate between those like parallel corpuses. And there have also been approaches where you don't do that and you just scale to have like more data, essentially.
I guess the latter way will be more prevailing because it's less effort.
Yeah, exactly. you have to do less to do that. But for example, I think Facebook, they have trained like these translation models. For example, one is called M2M, I think 100. And it's a translation model that can translate between 100 languages. And there they had to align the data sets. So they had to find like sentences in multiple languages that are what they call like parallel. But they did kind of like a cool approach. They used like their word embeddings. It's like a tool they call Laser, I think. And it's like word embeddings or sentence embeddings like in multiple languages. And they use that to kind of like take a big data set of multilingual data and finding sentences that are actually the same across multiple languages. And they synthetically created a huge data set with like word pairs for that, and they use that to train these language models, these translation models.
Thanks.
Sure. There's a question. There's a question about asking a question. Can we only ask questions related to the Transformers book? No, I think you can also ask other questions. Ideally, they're kind of related to the topics that we're talking about, but it doesn't need to be necessarily about like a certain topic in the book. So there's another question. Is token classifier output a requirement for the output of our custom NER model? Can you just return a dictionary with keys, slots, and digits? So I think you might be able to do that. It depends a little bit how much you want to use of the Transformers ecosystem. So I think, for example, if you use the trainer, I think it expects like these class, output class, to get like certain attributes from your model outputs. I'm not 100% sure, but I'm pretty sure that's the case. If you just use your model like in your own code and you have your own training loop, then if it's easier for you to deal with dictionaries, you can do that. That being said, the token classifier output class behaves kind of like a dictionary. So it's like, it has some additional functionality, but it's like very similar to a dictionary.
Leandro, I had a question.
Sure.
I think there's something like really interesting or profound about doing this task in the chapter. Like the fact that we can just train on lots of different languages and just generalize them is not very intuitive to me. So I was wondering if anyone has kind of figured out what the models are actually abstracting and learning when they are performing well across languages. Like, is there a linguistic rule or theory that's being learned inherently in the model that allows it to generalize so well? Or do we even know what's happening under the hood? That's kind of what I'm really curious about, because I don't think it's intuitive at all that this should work, beyond the fact that there are similar languages in the world and that they might use nouns or whatever similarly.
Yeah, that's a good point. I don't think I have like a very good answer to that. Maybe somebody else has. I mean, I can give you like my 2 cents, which is roughly that like these models, they have like limited capacity, right? And they have to learn a lot of things across a lot of languages, like 100 languages, and you have to learn things. So the one way you can efficiently do that is if you compress as much information as possible from these different languages, right? If you see similar patterns, and if you look at kind of like how, for example, people look at computer vision models, where if you look at the different layers, they start to abstract more and more, right, as you go deeper. So you start with like very superficial features, like in computer vision, it's like edges and corners and like textures. And as you go deeper, you go to more abstract attributes, like if there's a combination of these kind of edges, that's a face, or that's a bicycle or a car. And the way I think about it with like the transformer is similar, where you start with like superficial features, which are words, and then as you go deeper through the network, it probably abstracts in some way these like superficial features in more, let's say, like semantic representation of what things they are. Like, for example, older is an abstract meaning, right? That can be in many different words within the same language. So maybe they can learn similar things across languages. That's how I think about it, but it's not like founded in any observation. That's more my mental model at the moment.
That's fair. I just think it's a really interesting thought that I think it's important to press upon, you know?
I think that's related to interpretation of machine learning, deep learning. I mean, it has been in discussion for a while, but looks like there's no really great way to interpret. It's hard to interpret. It just works.
I think like the folks at Anthropic, they did like some great work recently on that topic, where they like less on like multilinguality, but more about like how transformers work. They looked at like simplified versions of transformers, like if it only has like one layer or two layers, can you like interpret what the attention is doing actually? And they have like really cool blog posts, but they're like weekends long. I think like 50 pages or so. It's more like a tiny book, but they're doing like some awesome work on that if you're interested in that.
Yeah, and that's pretty much why I was wondering that this is like pretty much like the shared responsibility model, but like shared responsibility model, not like for the cloud, but for NLP. And the reason why, because NLP like figures out some stuff, while on the other hand, it's still like your job to understand some of the linguistics to fine tune the models.
Yeah, I think there has also been a trend in that, right? Where it's like, I think 10 years ago or so, the way to do NLP was more coming from the linguistic side and try to like extract features that correspond to like things that we know they should correspond to, like trees of like the structure of sentences. And what happened a little bit with like LSTMs or later transformers is like, if you just throw a lot of data at it, it actually can learn these features themselves. So you don't need to handcraft them, which is both nice and gives the model more flexibility, right? Because it can extract the features that are interesting or useful.
And can I say that's the reason why we don't need to know a lot of linguistics knowledge in order to do the NLP work?
I think
I'm not sure that that's an accurate statement, though. You definitely need a lot of NLP, of linguistics knowledge to assess what models are doing, whether they're failing in ways that can be and should be avoided. But just to go back, Leandro, to what you were saying about how it used to be and how it is now, there's a talk by Ashish Vaswani, first authored on the attention paper, and he says very explicitly, like that was like early days before it exploded. He says that we did, like, this is proto quoting him, we did not come up with a good inductive bias for language. We came up with a good inductive bias for just like parallelizing all the layers. So like like there's this awareness that this is all data driven, that this is not like better than LSTMs on a theoretical level, because like theoretically, if you like close your eyes and forget all the successes, an LSTM is still a much better way to at least like theoretically model the sequence. It's just that it does not run well when you want to parallelize it on like 1,000 machines.
Yeah, I think that's also.
Sorry, go ahead.
No, go for it. I talk too much.
No, I had a question about are the objectives like the mass language modeling and predicting the next word in the sentence grounded in linguistics, or these are just objectives that people have thought of that leverage like sentence structure, which is, I guess, linguists in some way.
I think that they're probably like similar grounded to what Chris just said. Like it's just a very efficient and useful way to do things. And it turns out that these models actually learn quite a lot of things with these objectives, right? Like if you want to predict the next word or you want to predict the masked word, you have to know a little bit what's around it. But it's also, I don't think, like the end of the story. I think there have been like some work recently looking at that again. It's like, should it really just be one word? Should it be a span? Should it be like multiple spans? Things like that, where you try to make the task like better suited that the model learns more. It looks like Chris wants to say something.
No, I was just thinking about like how ad hoc it is to come up with these objectives. Because like moving from BERT to Roberta, people said, let's just drop next sentence prediction, and it worked better. Whereas like the intuition at the time was like, next sentence prediction, this is giving you like some sort of global coherence, and masking is giving you some sort of like local coherence. But it turns out that no. Something to do with lots of data is making it work for like the specific task, but
also shows you that it's like an empirical field, right? It's not like you can't, both also the next sentence prediction sounds like something that's reasonable, right? Like if you want to predict if something's next word, then probably you need to understand something about language. So let's add it.
Yeah.
Then you run some ablations, like, actually no.
Yeah, we're sort of like moving back to like the image of the experimental scientist, just like trying random things, and some things work, most things don't.
But I mean, for the masked language modeling, that wasn't like an entirely novel thing with the transformer. If you look at how word2vec is done, it's pretty much the same thing, right? Word2vec vectors are also learned by predicting like what's the word in the middle or predicting the surrounding word of a word. So like predicting words out of context has been like an objective like for a while. Well, one comment I wanted to make about your statement about the transformer its main strength being like efficient and parallelizable. It's like, have you read like the bitter lesson from Rich Sutton?
I have not, no.
It's like he's the guy who like kind of like the father of modern reinforcement learning. I think he's at DeepMind, and he wrote the reinforcement learning book. Essentially.
Yeah. I was just looking for it, just like I recognize the name.
And he wrote like an article, I think like 1 or 2 years ago, called "The Bitter Lesson," and it was exactly about the topic of like feature engineering and making models work. And he was saying like in the past, like, I don't know, 20 years or so, what has been proven to win all the time are the models that actually scale, not the models that are like smart crafted. So people try to come up with like handcrafted filters for CNNs and putting them together, but actually just making a very efficient architecture that's scalable and has like a good objective wins. And kind of like why the ResNet was so successful. And then also the transformers, like you can just throw more compute at it and it kind of scales quite efficiently, and you can see that it gets better. It's like the winning factor is like coming up with methods that are kind of simple and that scale good with like compute, like a winning combination. And he said it's bitter because as like a researcher, you think like, I'm gonna create that very smart feature. Like I was a data scientist before, where I worked like with tables also, and then you think like, I'm gonna come up with like a very smart way of describing like, I don't know, a customer. So, and then it turns out like if you have enough data, all these things that can be learned, and like feel defeated by a stupid algorithm.
Yeah, absolutely. I mean,
Leandro, could you talk a little bit about the body and the head? I saw in the chapter, in the sense, head is kind of allow you some flexibility to extend the functionality, to different tasks. I guess that's fine tuning, right? And the body might be just the pre-training. Am I right to say that? What's the fine line between the pre-training and the fine tuning?
Sure. So, I mean, when you pre-train a model, right, what you have is like you have the body is essentially all the layers of the model except like the last one. And if you do pre-training, the last layer, so at what goes through the layers is essentially like the representation of the tokens and the sentences that go into the model, and as they travel like through the model, these representations get refined in a sense. And in pre-training, at the very end, there is a layer that takes these representations and it has to predict the word, right? Either it's the masked word, or if it's like a model like GPT, it's the next word that you have to predict. But now, if you want to do classification, that last layer, just the shape of it, doesn't make any sense anymore, right? Because maybe you don't want to predict a token. Like a token prediction is essentially like very large classification. And so you can replace that layer, but you reuse everything else, and everything else has learned useful things, as we said before, right? Like just predicting the masked word helps the model learn like useful representations of tokens and tokens in their context. And you can reuse that if you want to do classification. So you just pick a new final layer to it. That has to be trained too, because that's usually just randomly initialized. But it's like less than 1% or so of all the weights that are in your model. So it's very efficient to train that, or very fast, let's say. Usually you still train all the weights because maybe the model can learn something new. But it's usually quite quick because most learning is happening in that last layer that's new. But that's what we in the book we called head, because it seems like fitting.
We can call this NER a head, right? Name recognition, name entity. This is the head, right?
Yeah. And there, like for all models, usually there are like many heads that you can choose. There's a classification head, there's a named entity recognition head. In other chapters, we use like a question answering head. That's more about like detecting spans instead of tokens. And one of the goals of the chapter was, because we actually show how that head looks like in code, is you can write your own head if you have your own task. So if you, I don't know, maybe you have like 3 classifications that you want to do in parallel, so you want to have like a special classification head, it's not that much code to come up with it.
Another question I have, this is also related to here. So when you initialize with the pre-training model, you initialize with the weight, but also the contextual embedding, right? You are using the contextual embedding trend from the pre-training model. Am I right?
Yeah, so the contextual weights are, I don't think they differ from the weights. So the weights of the model, they make the contextual embeddings later on. It's what goes into the models are just the tokens. And then their contextualized embeddings are built based on the weights of the models in other layers. So I wouldn't differentiate. I would just say like you have weights.
So you think they are interchangeable, the weight and the contextual embedding, they're the same or what?
So the contextual embedding is more the result of what comes out of the model. So what comes out of like each of these layers is like an embedding for each token that you have in your input. And these embeddings, they're computed when you pass a sentence or so. They're not like stored internally that you have like contextualized embedding for each word. Those are like inferred when you do like when you use the model. So they're more results. The weights are like storing the logic, and the contextualized embeddings are like the result of applying that logic to the input you have.
Okay.
I hope that doesn't confuse more than it clarifies.
It's still a little bit confusing. I guess I need to Google a little bit more.
Sure. Yeah, also feel free to ask more questions on Discord, so happy to try to answer. But yeah, contextualized embeddings is just means that's the representation of the word based on its surroundings that the model produces. And the way it produces it is with the weights. That's kind of the semantics, I would say. Let me see, are there any questions in the chat?
Yeah, and on the meantime, I would say something that I found interesting is how much like there are some like security issues there. And what I mean is that I think to some extent it's like similar like with executables, that basically when you have like big models like Roberta or anything for that matter, and you train those models, there are some like layers to attack, especially to put some backdoors in the base model. And this is also something that I've seen in the context of Hugging Face, because basically since Hugging Face is becoming like repository for models, I was wondering like whether like are you planning, or have you been wondering about like scanning the models, or basically like also like the vulnerability part of it?
So that's a very tough problem. There are several layers to that. So one thing you're mentioning is like kind of like robustness. So is the model like susceptible to kind of attacks? So you can make it do things that maybe you don't plan to have people do with it. I guess one example is like you train a model and you want it to be like create safe content, but depending on like how you prompt it or kind of like what words you input, you might still find ways to exploit it. I think every company these days that creates a demo of like a large language model faces that issue where like instantly thousands of people try to make the model output like the worst things that you can think of. That's like a really tough problem and a research problem. The other thing is, can you detect if somebody intentionally made a bad model, right? Maybe somebody trained a model just to create racist slurs. That's like similar. It's really hard to see from the weights of the model if that's happening. At the moment, the way it's done is mostly through reporting. So if people are reporting bad things, we try to moderate them in some sense. And the last thing is, which is probably like the more obvious like security issue, is the way, for example, PyTorch models are stored. They're usually like often pickled or something like that, and you can have executable code in those models, right? So when you load a model, actually some code can get executed, and that would be like pretty bad, because then you could say like, oh, look at my new awesome model, everybody should use that. And then you install like Trojan horses all over the community. For that last case, there are like a few things that we're doing. One is there's a security scanner on the hub. So if you upload things on the Hugging Face hub, the scanner goes through the files and sees if there's any malware embedded in the files that are uploaded. And we're working on a new library called Safe Tensors. That's like an alternative to saving models, PyTorch models, that doesn't allow for executable code to be in there. A fun fact is, like, I work like quite often with models for code, and I created some data sets for code, and they constantly get hit by the security scanner because there's a lot of malware on GitHub. And if you upload them to the hub, it lights up like a Christmas tree, and you can see all the files that have like security issues.
Yeah, and just to put like it more in context, the reason why I was wondering because Hugging Face like has the capability of like trending models or like models of the week. So I was wondering whether someone can create something like trendy that will become like trending, and by the time people realize that it's like malware, it will be already downloaded by many people. So I was basically wondering how much like also like the trending capability of Hugging Face is also at the same time like pretty much an attack vector.
I think the security scanner is pretty quick. So I think before something can become trending, it's very likely that the scanner has been gone through, and you should see like a red flag if there's like malware embedded. In the other cases, if it's just a model that produces like harmful content, then thus far, like the community has been pretty reactive with like flagging these models. But it's like a pretty hard problem, I would say. Like we're evolving the strategies as we go. Since we went from like having a few thousand models to like 100,000 models, like getting increasingly hard. I see there's another cat. Or
I have
a
a
tail of a cat.
Hello.
Yes.
Yeah, so my question is slightly open-ended, but is there a reason why only BERT-like encoder-only models seem to dominate in NAR and NER and classification tasks? And like, why don't we see like something like T5 or GPT-like models sort of giving us good results and benchmarks?
Mm-hmm. Sure. I can again give kind of like my intuition why that's so, but anybody who has like a different opinion is very like free to chime in. So the intuition behind like the encoder and decoder architecture, that's kind of like what T5 does, and the BERT models, they're kind of only an encoder model. T5 is an encoder decoder, and then you have GPT-3, that's like, or GPT-2, that's like just a decoder. And the way I think about encoder decoders is the goal of the encoder is to compress the information of like the input sentence into as much useful information as necessary, such that the decoder can do its job. And the job of the decoder is to take that information and start generating output text, right? In case of T5, you have like maybe a sentence in English and you want to translate to the French. So the goal of the encoder is compress like the semantic meaning of the English sentence in a useful format, such that the decoder can then generate the text from it, the target text, which would be French. So the goal of the decoder is to take a vector and create text from it. But for example, if you want to do named entity recognition, that step is not really needed, right? You don't need to generate text for named entity recognition. I think what T5 did, it kind of like rephrased some of the tasks that are like named entity recognition or classification as text to text tasks, but it doesn't need to be that way, and it's maybe like even like a step too far. And that's why like for many tasks that only require like understanding, like I would say classification and entity recognition or question answering, you only need the encoder part that takes like the input information, the input text, and compresses it into some useful vector, and then you add that final head to it that just does the task you want to do. And for other tasks like translation, I think these sequence to sequence models or encoder decoder models are what are dominating. And for like just text generation, I think GPT models that are only decoder are dominating. But you can kind of like abuse any of the architecture for any of the other tasks, right? You can also use GPT-2 to do few-shot classification. But I think the reason why like BERT models are still like competitive with models that are like 100 times bigger is that their architecture is like just very tuned for that type of task. Does that answer your question?
Yeah, thanks. A follow-up question though. So like if let's say we chop off the decoder part of a T5 and only use the encoder. Do you think it will perform better or worse than the entire model? Considering that encoder decoder models actually are double the parameter size, right? So like, is it something specific about just the encoder and a classification head that makes it so good?
Good question. I don't know if anybody has done that, but I would expect that it could work in general. I guess it depends a little bit on like how much data you have, because like the objective of T5 is kind of quite different from an objective that a BERT-like model has. And if you then just want to fine tune the encoder on something like that, maybe you need a little bit more data than a model that has been already pre-trained with that objective. But it wouldn't be that hard, I think, to run an experiment.
If I may interject, so I don't know about whether this has been done on T5, but I know that it has been done on MBART. So this is also an encoder decoder transformer, and the decoder has been used as part of a speech recognition task. So basically having a speech encoder and reusing the decoder from BART. So that seems to work extremely well just by retraining the cross attention. And yeah, you can do multiple things, of course, like adding adapters between the encoder or the decoder, or just using the output of the encoder as is. And it seems to work well. It works quite well.
That sounds interesting. Could you possibly give me a paper link for that work?
Oh yeah, sure. I will send it in the chat.
Thanks.
Thanks for sharing. Let me see. There another question. Mainly about cats.
Can't believe I missed it.
Do any reference-free metrics exist for NER multilingual NER task leverage besides the reference-based metrics mentioned in the book? Also, what are your thoughts on reference-free metrics while working on Evaluate when you come across some metrics designed to be reference-free by nature developments in the field? Good question. So I think about it, but I don't think I know of any like good reference-free metrics for NER or multilingual NER on the top of my head. And I think in general, like for many supervised tasks, like reference metrics are useful in the sense that, I mean, the tough part usually is figuring out which one is the right metric to use. But once you have like a metric that you're confident about reflects what you're trying to achieve, they're pretty efficient then at measuring that. But to be honest, I haven't been using or seeing reference-free metrics for supervised tasks that much. Yeah, I don't think I have much more knowledge I can share on that topic, sorry. A reference-free metric, I think, is a metric that doesn't come with a label. So you try to measure how good your predictions are without having access to like gold labels. Cool. Are there any other questions or things you want to discuss? I still have a couple of minutes. Can also
I
talk
have
about cats.
one.
Sure.
Yeah, I have a
about cats?
question. No. We can talk about cats later.
No, now.
I have a question regarding memory mapping, which is the mechanism which like the datasets library uses. So I want to know if it makes if memory mapping only makes sense when you is more efficient when you cannot load your data set in memory, or is it more efficient overall?
So it comes with a trade-off, right? Because the memory is not as fast as disk in general, right? So if you want to do certain things, if you load them into memory, you can do things faster than if you have to go to memory sometimes and read some data. That being said, for example, if you work in NLP, usually you're not constrained by speed of processing. Like processing text is like super fast, right? Applying regex to a terabyte of data is not the problem. It's like loading a terabyte of data in memory. That's usually where the bottleneck is. In the datasets library, you can do both. You can also load the data in memory if you want. I think there's a flag that you can use if like speed is an issue.
But how would you load the data in memory if you have a 1 TB data set? Then
then you can't.
Right. So that is that. My question is that where memory mapping helps as opposed to. Okay.
Yeah. So the main cool feature of memory mapping is you don't need any memory to do your operations, right? You load data kind of on demand into memory.
Okay.
Which can be an issue with certain modalities, usually with text. That's not the main bottleneck. Yeah. But yeah, it's the main selling point is you don't need to keep your data in memory.
Okay. And maybe a tangential question. If say I want to run 5 experiments on one machine, and all of the 5 experiments are using one data set which can be loaded in memory, is there any library that can help me do that? Because if I launch it in multiple times, then that data set will get launched 5 times. That data set will get loaded into memory 5 times. But I want all 5 training runs to reference that one memory, one data set loaded in memory.
So you essentially want to share your memory across processes.
Okay.
I don't know. I think, just doing it naively seems to be a hard problem. I don't think you can easily access the memory of another process. Like if it's just pure Python, what I could imagine could work if you run like kind of a server or like a process that's accessible as like a server where you can like call and it gives you some data. If that makes sense, where you spin up one Python process that loads the data, and you can call that Python service, or how you want to call it, and it gives you like data, and multiple processes can do it.
But if your worry is to not load the data set multiple times, if you're using like the Hugging Face data set, it's going to be the same exact arrow table on disk that's being used.
Right, but if I have 5 Python processes running, won't they? And the Hugging Face data set is memory mapped, so it will only load data on demand. Won't my memory consumption increase as I increase the number of training runs?
But you won't use any memory for any process, right? Because they only load the data that they currently need. Or am I misunderstanding? Because they're all memory mapped.
Right, they're all memory mapped. So let's say process A launches one like indices 1 to 5 in my data set. Process B is at a training stage where it's loading 5 to 10 indices in my data set, and that portion of the data set loaded in memory before before you process them? I guess I need to draw it out to explain it.
Yeah, so you're meaning like you essentially process a different batch on each process, and so if you have 5 processes, you might have 5 batches in memory at a certain point. Yeah, that sounds about right, I think.
Okay. But I think what you suggested would work is have a separate Python process that sort of serves that data in memory, and have the other processes talk to that process somehow.
Yeah, that would be like, I mean, with something like Fast API, you can build like a prototype pretty quickly. That's like just something that you can call from another Python process. But yeah, I think it depends a lot on like how the concrete setup is in terms of like bandwidth and data you need to send around, where these things might break down. Also, it would be interesting to see if it works in data sets, or if you can make it work in data sets. So if you can share some example or code, I'm also happy to like give it a shot.
Yeah, I can share some. Share it out.
Cool. I think we're already a few minutes over time. That went quickly. Thanks everyone for joining. I'll put up another survey for the next chapter in Discord. I think we have like probably one more session we can do before Christmas. So Chris can wear his Christmas sweater again.
What?
And gets another chance at seeing cats.
No, I'll wear the other one.
Nice.
What do we still have to vote on? I remember text generation still being up for voting, and
I mean, now that we did a few, maybe we can add some more to the pool. I mean, as I said, I think so far we went like in order through the book, but we don't necessarily need to do it that way. But it seems like that's what people want to do, so happy to follow along.
All right.
If it were up to me, I would start at the end and reach forward.
What's the end? Well, like the index?
Yes. Let's go through the index.
N-gram penalty. Page 133. N-grams 152.
Ooh.
Leandro, I have a short question. Like, if you save model, Hugging Face save a lot of model. Of course, you save the parameters. It's back to my original question. Like, suppose, like GPT, you have 175 billion or whatever parameter, you save that. But suppose you train the model on certain corpus and you have a vocabulary. Suppose I make up a number, 100,000 vocabulary, the size. So where do you save? Do you save the contextual embedding for the 110,000, 100,000 token after the training, or you only save the parameter and the architecture of the model?
So those are saved in like 2 pieces. One is the tokenizer, that was one thing, which is related to like the vocabulary, and the other thing is the weights of the model that are also saved. But I think post the question, if that's not clear, post the question on Discord and then we can continue there. Sorry, Chris, do you want to say something?
I just wanted to ask what you mean by contextual embeddings. It could be that we're like thinking of different things when you say contextual embeddings. Could it be that you mean the input embedding matrix that turns like the one-hot vectors into a dense vector? Is this what you?
Yeah, that's what I mean. I mean,
this is not a contextual embedding. This is a static lookup style embedding. Every word in the vocabulary gets mapped to the same vector every time. And this is just a static matrix.
But after this mapping, after the training, each token will be associated with a dense vector of certain dimension, like a 768 or whatever.
Yes.
So that's what I mean, the embedding.
Yeah, that's
stored with the model.
Yep.
It's stored with the model, right?
Yep.
Yeah.
Oh, okay. Okay, that's what I want to know. Yeah. Thank you.
Usually people call that like the embedding matrix.
Yeah.
Because
okay.
it's not contextualized embeddings at this
Yeah.
point yet.
Or input embeddings sometimes also.
Okay. Good. Nice.
All right.
Okay.
All right.
Have a nice evening. Have a nice day, and see you in 2 weeks.
Bye,
Bye,
everyone.
everyone.
Thanks. Bye, guys.
Thanks for
Bye,
joining.
everybody.
Thank you.